Yeah, hello everybody. So the work I'm going to present is joint work with Kamil Jacek from the University of Western Bohemia, who's also in the audience over there. Yeah, motivation. So when you have a program in Java, and we consider mainly Java here, even though many of our findings could be generalized to other languages and virtual machine runtime environments. So when you have a Java program, typically use libraries. So the most straightforward scenario is you have a call site in your program and you call a function in the library. And now what happens if the library changes, if the library evolves into a new version 2, let's say? That is actually two questions you have to answer here if you want to establish whether that is compatible, because first you could consider that you recompile the program against the new version of the library, or that you just upgrade the binary of the library and redeploy those. And actually the second approach is becoming more and more common as people use automated dependency resolution tools such as Maven, Cradle, or platforms such as OSGI. So there are two questions to answer. Do we have source compatibility, so can we recompile against version 2 of the library, and do we have binary compatibility, can we relink with version 2 of the library? So typically those things are pretty consistent. However, there are cases when they are not, and that example shows such a case. So now we have a call site for a method called foo, and now in the target library we wish to use, we change the return type of this library by replacing collection to list. So a list is a subtype of collection, so if you ask a programmer what he thinks about this, he will say, well, there's no problem there. We specialize the return type, so we keep all the promises. So we strengthen the post conditions, and that's compatible. And indeed, if you compile this, that is actually exactly what happens. You can recompile a program with version 2 of the library. However, if you just replace the binary, then you suddenly have an error, and that is manifested by a so-called no such method error. And the deeper reason that you get this error is that at the call site, the method reference is represented what's called a descriptor, and that is a combination of parameter types and the return type. And of course, in this case, the descriptor changes from the first line over here to the second line that has the new return type. You can actually construct similar examples that show that you have scenarios that are not source compatible but binary compatible as well. So those two notions really don't match. An example for this is if you have a method and you evolve the method by introducing, for instance, a checked exceptions, and you get the opposite scenario. So I think the bigger picture is that for many years now, the innovation on the Java platform has focused on scalability, security, fault tolerance, and all those things, but had a very strong objective to keep the structure of the bytecode and as stable as possible and as compatible as possible to existing programs. Whereas the language innovation focused on program productivity, often driven by features you would have in other more modern or more sexy languages such as Scala and Ruby, often implemented by means of syntactic sugars that the compiler would actually compile away some of the features you had in the source language. Generics, boxing, unboxing, covariant return types are examples for this. So in a way, the mismatch between binary and source compatibility reflects this a little bit from the point of view of the programmer. So the question is, how do developers cope with this? And apparently not very well. And in the last 2 or 3 years, there were a couple of studies done by us and by a couple of other groups, in particular by a group in Delft, who have tried to explore API stability. And it turns out that APIs in Java programs are not very stable. So there are libraries which are very, very widely used, such as Endler and Hibernate JUnit, that are API instable, meaning that they have public methods where the signatures change from version to version without this being flagged or being reflected, for instance, in the version numbers that is being used. So we also conducted a study where we actually quizzed developers about this, and we had a really good response rate. So we quizzed over 400 commercial developers and gave some little quizzes where we asked them, do you think this scenario is source and binary compatible? And it turns out that people really lack knowledge about binary compatibility, but have really good knowledge about source compatibility. So that's really motivated us to try to address this issue. Well, there's one more point I've almost forgotten. So you can actually also look into problems caused by binary compatibilities that usually manifested by certain linkage errors, and then you can just look into issue tracking systems, how common they are. And it turns out that those problems are as common as, for instance, class cast exceptions, which is somehow surprising. So it has a lot of hidden pain here. So the plan we came up with to solve this problem was to improve the consistency between compile and linker, to compile cross-component calls differently, and therefore to reduce link-related errors in real-world programs. So we set out to address a number of evolution patterns which are compatible from the compiler point of view but cause binary incompatibility. For instance, if you change a non-static method to a static method, if you box, unbox, widen, or generalize a parameter type, or if you box, unbox, narrow, or specialize a return type of a method. So those are the evolution patterns we wanted to support and where we wanted to avoid binary compatibility problems. We initially considered a couple of different options to tackle this problem. I think if we had protocols like does not understand, then that would be a viable route to implement this. Other possible approaches would include the use of adapters or proxies, which all have certain disadvantages in terms of performance overhead, and proxies maybe have to be deployed and generated. We could also, of course, change the entire JVM, take a research JVM, try to re-implement the linker, which is, of course, very invasive and very complex to do. One overruling design goal was to have transparency for both client and libraries. What I meant by this is that neither programmers that programs that has the call side for the library code, nor the provider of the library code actually has to annotate the code in order to initiate any special handling, because it turns out that neither of them really understands how binary compatibility works, right? So we wanted it to have to be completely transparent, so we needed some magic. So to the rescue came Invokedynamic. That is a new instruction in the JVM instruction set that was introduced in Java 7. It was, I think, originally introduced in order to facilitate the implementation of dynamic languages on the JVM, such as Ruby, and is now also used to compile lambdas. So the way that works is basically as follows. So you have a call side, and the call side you have a reference to a user-defined Bootstrap method, and the Bootstrap method is then used at runtime, or rather at link time, to compute what's called a method handle. That's the representation of the actual target method, and this entire chain gives you more control over the dispatch process than what you would usually have with the classic invoke instructions. So a good way to think about this is as follows. So when you resolve a method reference, you have to do two things. First, you have to come up with a descriptor and the name of the target method, so that is usually quite easily done, and that's typically done by the compiler. And then once you have the descriptor and the name, you know what kind of method you're looking for, and then at runtime you actually look for the actual method that fits the respective name and descriptor. With Invokedynamic, you have actually some control over the first phase as well to do some sort of custom user-defined behavior and implement it there. So the piece of software we have now built is called Dynamo, and it actually has three components. The first one is, well, you could see it as a bytecode instrumentation framework. And the way that works is you take existing bytecode and you modify the bytecode for cross-component call sides. So we are really looking for invoke static, invoke special, invoke virtual, and invoke interface instructions, and try to replace them by new Invokedynamic instructions. So to do this, we have to construct what's called the Invokedynamic call side specifier from the original invoke instruction we find and replace. And to do this, we have to provide a reference to a Bootstrap method. So here are some examples to explain this. So in the first call, we just invoke a method setValue with an integer parameter. So we push this onto the stack, and then we call invoke virtual and the Invokedynamic instruction. That replaces this is very, very similar. Please note that that's essentially the first parameter, which represents the class that defines the respective method. That works pretty well for most instructions, but it's slightly more complex for invoke special, and the reason is that invoke special is actually used in different places. So you use it for private invocations, for invocations via super. Those are easy to handle because private invocations cannot, or invocations of private methods cannot be cross-component by definition. So we can actually ignore them. Invocations via super, we can just handle them via like invoke virtual. For constructor invocations that show up in bytecode as invocations of a method with this magic name in it, we must detect a so-called bytecode behavior. So here, for instance, if we call a constructor of a class C with a certain parameter, we calls a new instruction to create a new object, then we duplicate the reference on the stack, then we call the constructor code that consumes one copy from the stack, but then another copy has to be there to assign it to a variable. That's why you have to duplicate this. So basically, we have to replace this by a single Invokedynamic and recognize this pattern and generate an instruction that looks like this. And that is possible, and we are doing this. Once we have the enhancer component that just replaces the instructions, we can very, very easily, with a simple trick, turn it into a compiler. And to do so, we just use the standard Java compiler, which we can access through an API, which is JSR199. So basically, we use the standard compiler, compile in memories, and do the bytecode instrumentation, and then write out to the file system. So that's really a very, very simple trick, but it gives us compilers that has a lot of the characteristics in terms of performance and reliability of the standard Java compiler. There's a special parameter that can be used to customize what to compile, special, or which instructions to replace. And I'm not going into details here. That is just a little DSL that can be used where you can actually, on both sides, on the call side and on the target side, actually specify with certain simple patterns with wildcards what to include and what to exclude. So for instance, you might want to know there's a certain library I'm using, but I know those guys really know about binary compatibility and are very disciplined in versioning their code, so I really trust them that there are no incompatible changes expected, so you want to exclude this. And you can do this with this kind of parameters. The Bootstrap methods, that is actually now the third component. At runtime, of course, you have to resolve the Bootstrap methods, and you have to recreate some of the logics that is usually done during compile time. So the functionality is provided by a little runtime component we have written, and that uses the Bootstrap methods to compute instances of a Java class called callSide, and the callSide then produces method handles, which are references to the actual target methods. And that is only done once, and this entire chain is set up in a way that most of the JVM optimizations are still available. So Invokedynamic is nowadays very, very fast. So that was one of the advantages of choosing it in the first place. So the process of runtime resolution is actually quite a tricky one. So the overall target is to do this in a way that we keep it as similar and consistent with how the compiler operates as possible. So we want to find a method that is similar to the target of the replaced invoke. So we deal with ambiguity, so we try to locate a unique best fit. To do this, we have developed a little conceptual model that simplifies the rather long and complicated rules in the Java language specification on how conversion and resolution takes place. So that is a graph-based model. Unfortunately, the resolution isn't very good, but basically I try to explain it with some examples. So we have subtype relationships. For instance, serializable is a subtype of object, and somewhere here, array list is a subtype of list. So those are labeled with a little errors. And we have boxing and unboxing. For instance, here we have those relationships between the primitive type double and the respective wrapper class double. And then we have what is it for instance? Here is a widening relationship where an int is widened to a double. So once we have this, we can express type compatibility that in particular includes boxing, unboxing by reachability in this graph. It's actually not quite that simple because there are certain patterns formed by paths in this graph that are illegal according to the Java language specification. I skip a discussion on this because it probably takes too long, but you can actually describe what is legal with a relatively simple pattern. So the programming language or the static analysis community uses this for context-free language reachability. You know, it's a similar way to express this, so that the paths that are valid in this graph have labels that have to form a pattern with respect to a certain grammar, and that's really the grammar here. That's actually more simple than it sounds. Then we can extend adaptability to descriptors and different directions for parameter and return types. So we have co and contra variants there. So we also add the owner to the descriptor, and that is something we just give it a name. We call it the extensive descriptor XD. And so we have a very simple setup that allows us to create a partial order what is adaptable between extended descriptors. And here are a couple of examples that explain this probably better. So collection or method foo that returns a collection is adaptable to foo that returns a list because it's a subtype. We can also generalize the parameter type or box the parameter, or what do we do here? We first box it, and then we generalize this, so we can actually compose those conversion rules. That's really what the reachability is doing. Okay, so there are a couple of examples for this. Then we have runtime resolution rules, and they again closely resemble how the compiler operates. So the first one, we only pick user-defined methods with a matching name, so we don't change the name, and we don't target synthetic methods. That is quite important in some examples, in particular in the second case study I hopefully have time to talk about briefly. Then we pick the most specific adaptable method with respect to this adaptability partial order we just introduced. And then we try to resolve ambiguity, and there's again a rule we adopted from the rules in the language specifications that's used by the compiler. If you have multiple candidates, multiple minimal models with respect to this order, and they have the same parameter types, but one has a more specific return types, then we use this one. And that again is very, very useful to deal with certain scenarios we observed. And if that all fails, we just create a linkage error. We create a no such method error, which is already defined in the Java core libraries. Yeah. So here's an ambiguity example. For instance, we have a method that has an array list parameter type, and it is replaced now by two methods. One has a serializable parameter type, the other one abstract list. That would actually fail because we cannot work out a most specific target method. So then we did some validations. There's a set of benchmarks where we looked for micro benchmarks to measure the compilation time and the runtime overhead. And given that I only have 3-4 minutes remaining now, so I just quickly walk through this. So the overhead we found and measured is actually very, very minimal for the micro benchmarks for both compile time and runtime. Then we have two case studies. The first one is actually a real-world scenario which we observed in one of the preview studies. So there's an open source library called jasperreport that uses another open source library called jfreechart. And here in jfreechart you have API change where you just change a constructor by generalizing the parameter type, and that actually creates a linkage in no such method error. And again, as I said earlier, if you go to Stack Overflow or platforms like this, that is full of reports of errors like this, because you have incompatible API evolutions. There is a second, and we fix this by just compiling with Dynamo. There's a second case study, and that takes some time to explain this, but I would really invite everybody to have a look at this, because that is a scenario that was reported in the Java developer mailing list first, when the engineer started to refactor clone to use covariant return types. If you have covariant return types in Java, you introduce a so-called bridge method that has the same parameter types than the original method, but a different return type. And if you have a deep hierarchy that goes over two libraries and you refactor this in a certain order, then suddenly you have three features that are thought to be completely orthogonal. You have dynamic dispatch, you have bridge methods, you have to think about, and covariant return type. So sorry, that's the language side of bridge methods. And suddenly, if you combine them in a certain order, then you get a Stack Overflow, because the lookup fails and you're kind of caught in this call graph loop. It's a very bizarre example, but it's a real world example, and we actually solved this by just compiling with Dynamo and by using a different solution. And that was indeed the last free slide. Conclusion future work. We believe that code evolution is very interesting and is maybe underrated. There's maybe some interesting work for the program language community here to take evolution into account. Our colleagues talked a little about contracts earlier. We are quite interested in this, so that what we observed here just shows that there are different types of contracts between a method calling another method and the target. And you could also now observe completely different types of contracts, like quality of service contracts or licensing contracts, and then validate software against this, also verify software against this. And a particularly interesting question we started to get interested in is how do those contracts evolve. So what happens, for instance, if you implement a new language that has a very desirable feature like a verifying compiler, you do static analysis, but then suddenly you can undermine the contract checks by just evolving the library, by just replacing the library by a new binary, right? So one particular area we want to go into and want to extend this work is actually the use of semantic versioning. There's a lot of movements here in industry where people try to compress complex contracts into very, very simple contracts that are easy comprehensible to developers by just squeezing them into those recursion numbers, but just compute and verify those versions instead of assigning them manually. So, and that's definitely the last slide. I would like to thank a couple of people, Alex Buckley, Alex Botanin, and Nick Hollingham, Oracle Labs, for funding me. Actually, they funded me for another project, but that's still very useful. And finally, there was a pun in the title. I'm not quite sure whether everybody got this. So there's a famous British magician called Dynamo, which is also quite famous in New Zealand, actually. So, and hopefully we're not getting sued for using this in the title. Okay.
Any question for Jens?
So thank you for an interesting talk. I was wondering, why is it Dynamo? Why would it be done? Couldn't it be done statically? Because what you do is you do pattern matching on. Let me repeat the question. I'm asking that I like Dynamo very much, and I'm asking why couldn't it be made statically? In other words, you have method calls in one library, one component, and then you have the method offered by another library, and you try to bring these into these by lots of widening, boxing, unwidening, etc., subtyping. So presumably you could have done all that in compile time when you try to...
We don't know the target library. The target library changes.
Yeah, but what's
that is a problem, yeah? So we try to do as much as we can at compile time with the Invokedynamic instruction, but actually the binary can change at runtime.
So yeah, I understand.
Yeah.
What I mean is that you could generate, when you could link them together, you could do everything at link time, couldn't you? When you put, if you have the Maven thing,
right.
Maven downloads a newer version of the library.
Yes.
So you could activate your engine, and your engine could generate the bridge code for one component to another. So it could be part of the deployment, the Maven processing.
Right. It could generate this. That might be true, but there are also scenarios that are completely dynamic. OSGI maybe comes to mind, where you would not have the chance to create static code for this. Our platform would still work in this scenario.
Right. It only could work with Maven and stuff like that.
Yeah.
Yeah, thanks for the nice talk. So I was wondering, if I understood correctly, your assumption is that there's some developer or user that specifies what is part of the API that accesses other libraries and so on, and because you're not then turning into dynamic calls every single method call, right? There are certain calls that are being transformed.
There are calls that go across the library.
Yeah, so how are these specified by hand, or how do you identify those?
Well, at compile time, you give a parameter to the compiler that sets the class path for compilation. And then you actually know where the classes are coming from. And then you say if the classes are coming from an external jar, then it's an external library, then you check the filters whether you want to exclude this or not.
Yeah.
And if not, you replace the respective calls. You know where the classes are coming from. You know which classes are part of your project, which classes are external. And for the external classes, you compile differently.
No, I understand. Okay, thanks.
Thank you for a very interesting talk. I was particularly intrigued about your idea that you could address the problem by better language design.
Yeah.
However, on the other hand, I don't see why, because, or I would like you to explain a little bit more. You said if we had contracts between caller and callee and the contracts evolve, then perhaps we can address it better. But that's exactly what is happening with binary compatibility issues. The contract between the caller and the callee is the type of the function, and then the type of the function changes, and the caller doesn't recognize it anymore, or doesn't find it, and you have to provide the bridge code.
Yeah.
So, if we consider that types are contracts, I don't see how contracts could help us, or please explain how contracts would be better than types.
Okay, so particular contract, and maybe to some extent I have a certain industry perspective here. The way developers use contracts very often now is through semantic versioning. So you use a library through a system such as Maven. And you say, okay, I use library foo and I use version 1, 2, 3. And then you can make a certain assumption about compatibility. For instance, by saying, I specify a dependency to this library as being dependent on version 1, 2 star, because the assumption is that the developer of the library uses semantic versioning, and everything that has a star only at the last, everything that only changes the micro version will not change the API. That is the theory of semantic versioning, and that is how it's supposed to work. But it's not working like this at the moment, because the developers have the responsibility to assign these versions manually, and they don't cope with the complexity. But that's a problem that can be solved. For instance, if you build a diff tool even just based on the rules of binary compatibility, you can say, well, I have my version of code here, I have the older version of code, I run this tool and I compute the next version. Because then you can actually rely on this. You have a very condensed contract and you can use it for decision making. But it's not just about the type system, and you could even now think further, what about semantics, what about pre-post conditions? Yeah, that would be nice. But it's even other things, what happens, for instance, if you have a target library and the developer decides to change the license of the target library from Apache to GPL. Is this a contract breach? I think it is. Yeah. So I think there's a lot of reasoning and inference about those things required to facilitate a world where software changes very, very quickly and very, very often, and a lot of the processes are automated through things like Maven, for instance. People don't do this manually anymore to collect together libraries. They have the declarative dependencies, and they are resolved by tools. Very deep dependencies, transitive dependencies. Yeah, so I think that is where maybe as a community we could provide more support.
Okay, so just one more quick question.
Yeah, thanks for the nice talk. Could you speculate about how you could look at compatibility with generics? Because you change your API to take a list of integer and change it to a list of int. The bytecode signature of that actually doesn't change. And so you get some class cast exception somewhere while you're executing the code.
Right.
Could you somehow use Dynamo to, instead of having that error happen inside the call method?
Maybe you have information missing on the call side, yeah, if you do this. Yeah, so we have the problem. So I talked about the collected problems in a kind of catalog as puzzles we then used to quiz developers. So we have a couple of interesting examples based on generics, but I do not know how to extend the solution to generics. That would be very nice, but I don't think there's enough information there. So interestingly, you have scenarios where if you look at an example, you think that should be binary incompatible, but it's not. As I said, you get class casts. So in a way, there's a fuzzy line between binary and behavioral compatibility, right? I don't think you can solve it that easy.
Thank you.
Okay, so let's thank Jens again.
Yeah.